There is a hole at the bottom of math. A hole that means we will never know everything with certainty. There will always be true statements that cannot be proven. Now, no one knows what those statements are exactly, but they could be something like the twin prime conjecture. Twin primes are prime numbers that are separated by just one number, like 11 and 13, or 17 and 19. And as you go up the number line, primes occur less frequently, and twin primes are rarer still. But the twin prime conjecture is that there are infinitely many twin primes. You never run out. As of right now, no one has proven this conjecture true or false.
But the crazy thing is this: we may never know. Because what has been proven is that in any system of mathematics where you can do basic arithmetic, there will always be true statements that are impossible to prove. That is life.
Specifically, this is the game of life, created in 1970 by mathematician John Conway. Sadly, he passed away in 2020 from COVID-19. Conway's game of life is played on an infinite grid of square cells, each of which is either live or dead. And there are only two rules. 1, any dead cell with exactly 3 neighbors comes to life. And 2, any living cell with less than 2 or more than 3 neighbors dies. Once you've set up the initial arrangement of cells, the 2 rules are applied to create the next generation, and then the one after that, and the one after that, and so on. It's totally automatic. Conway called it a zero-player game. But even though the rules are simple, the game itself can generate a wide variety of behavior. Some patterns are stable. Once they arise, they never change. Others oscillate back and forth in a loop. A few can travel across the grid forever, like this glider here. Many patterns just fizzle out. But a few keep growing forever. They keep generating new cells. Now, you would think that given the simple rules of the game, you could just look at any pattern and determine what will happen to it. Will it eventually reach a steady state? Or will it keep growing without limit? But it turns out this question is impossible to answer. The ultimate fate of a pattern in Conway's game of life is undecidable, meaning there is no possible algorithm that is guaranteed to answer the question in a finite amount of time. You could always just try running the pattern and see what happens. I mean, the rules of the game are a kind of algorithm after all, but that's not guaranteed to give you an answer either, because even if you run it for 1 million generations, you won't be able to say whether it'll last forever or just 2 million generations, or 1 billion, or a Googleplex. Is there something special about the game of life that makes it undecidable? Nope. There are actually a huge number of systems that are undecidable, like Wang tiles, quantum physics, airline ticketing systems, and even Magic the Gathering.
To understand how undecidability shows up in all of these places, we have to go back 150 years to a full-blown revolt in mathematics.
In 1874, Georg Cantor, a German mathematician, published a paper that launched a new branch of mathematics called set theory. A set is just a well-defined collection of things. So the 2 shoes on your feet are a set, as are all the planetariums in the world. There's a set with nothing in it, the empty set, and a set with everything in it. Now, Cantor was thinking about sets of numbers, like natural numbers, positive integers like 1, 2, 3, 4, and so on, and real numbers, which include fractions like 1/3, 5/2, and also irrational numbers like pi, e, and the square root of 2. Basically, any number that can be represented as an infinite decimal. He wondered, are there more natural numbers? Or more real numbers between 0 and 1? The answer might seem obvious. There are an infinite number of each, so both sets should be the same size. But to check this logic, Cantor imagined writing down an infinite list, matching up each natural number on one side with a real number between 0 and 1 on the other. Now, since each real number is an infinite decimal, there is no first one, so we can just write them down in any random order. The key is to make sure we get them all with no duplicates and line them up one-to-one with an integer. If we can do that with none left over, well then we know that the set of natural numbers and the set of real numbers between 0 and 1 are the same size. So assume we've done that. We have a complete infinite list with each integer acting like an index number, a unique identifier for each real number on the list. Now, Cantor says, start writing down a new real number. And the way we're going to do it is by taking the first digit of the first number and adding 1. And then take the second digit of the second number and again add 1. Take the third digit of the third number, add 1. And keep doing this all the way down the list. If the digit is a 9, just roll it back to an 8. And by the end of this process, you'll have a real number between 0 and 1. But here's the thing. This number won't appear anywhere on our list. It's different from the first number in the first decimal place, different from the second number in the second decimal place, and so on down the line. It has to be different from every number on the list by at least one digit, the number on the diagonal. That's why this is called Cantor's diagonalization proof. It shows there must be more real numbers between 0 and 1 than there are natural numbers extending out to infinity. So not all infinities are the same size.
I don't know how they match every real number with the integer though. If it's infinitely from both, it will just keep running. How will they match that? I don't understand.